Boom.
Good morning, ladies and gentlemen. Today we are going to learn about cats.
Cats!
Meow. Okay, first pause the video and do this question.
Pause it.
Okay, now that you know what to do, let's do it. Number 115, number 38. The first one right here. A 35 kilogram crate rests on a horizontal floor, and a 65 kilogram person is standing on the crate. Determine the magnitude of the normal force that A, the floor exerts on the crate, and that the crate exerts on the floor.
Nope, on the person.
On the person, sorry. I was reading the other section. Okay, so what do we start off with first here? Let's draw what we've got going on here. So we've got floor, and crate, and then person, woohoo, which was 65 kilograms, right?
Yeah.
If we add those two masses together, what do we get? Looks to be like 100, yeah?
Yep.
Okay. So now we've got our diagram. Let's go ahead and do our free body diagram.
Good
since
idea.
We've got our sketch. Okay, so let's represent this whole system by a dot. And what forces do we have going on here?
Well, 100 kilograms, you got a force of gravity down.
Okay, so that means I'll call this my weight equals m times g. My mass is 100 total times the force of gravity, so that's going to be negative 1,000 newtons.
1,000 newtons.
Okay, what else do we have here? If we've got something down, we must also have something
Well, it's not accelerating, it's just sitting there.
just chilling, so it must be up.
So, what do you call that?
We call this the normal force. And what do we know about the normal force? It is equal in size but opposite in direction.
So, is that the first question?
Yeah, so it says determine the magnitude of the normal force that the floor exerts on the crate.
Yep, got that.
Okay,
That's A.
that's A. And that the crate exerts on the person.
Okay, now this is different here.
Okay, so how do we do this one?
Well, now we got the person.
I want to focus on the person now. So here we go. So what do we know about the weight of our person? How can we calculate that?
It looks like he's 65 kilograms.
65 times negative 10, so right?
Yep,
Negative 650. So that's the force of gravity.
yep.
Now again, force by normal force is just going to be the opposite of that, right? That's the number on the scale, right?
Yep, he's not falling through the crate, so that must be it.
Okay, so
Simple.
that is going to be the crate on the person. Done. Okay. Mark a spot on the table to place the block every time. Let's do a lab here. How can we find...
Bring your mouse.
Oh, yeah. Use the scale to slowly increase horizontal force on the empty block until it first moves. Note the force.
Make a data table, boys and girls. It'll look like this.
So we want to find the force, the max amount just before it moves. So you're gonna zoom in on that for me real quick, real close, right? This side, that's what we want. Right here, okay. All right,
Good.
here we go. Oh,
That was about 3.8.
that's what I saw too. Okay.
Write that down.
So write this down. That was for when it was empty. 3.8. Can you see that all right?
Yep.
Okay. And then now place the 1 kilogram mass in the block and repeat. What is different about the force? Here we go.
Whoa! That was more than 5.
Yeah. Should we use the other one? Or is this
Nah,
one fine?
we'll call it 5.2.
Okay, 5.2. Okay, 5.2. Make it look like this.
That's more.
Definitely more. Okay, last one here. Place a single sheet under the block and repeat. Okay, put it right there. Put this back in here. Oh yeah, it's probably a good idea. Okay, here we go. You ready for me?
Go.
Oh, did you see which one it was?
That was about, what, 4.4?
4.4.
Yeah, I'd say 4.4.
Oh, right. Let's go ahead and write this in. What do you notice about the force of that one? A little less, right?
Absolutely.
The force of friction, F of F, is a force that resists motion, and there are two kinds. Thank you. Static friction,
Stiction?
resists the onset of motion, static, not moving. So we've got static friction and kinetic or dynamic friction, sliding friction,
Sliction.
resists motion while in motion. So
There's two kinds, if it's moving and if it's not moving.
How much friction depends on two things we have to take into account. How tightly the two surfaces are squeezed together.
Didn't we see that?
Yeah, we saw that. And that's what we just saw over here, right? We saw that for the first one we had just the block on the table, right?
Yep.
And then for the second one, we added in our 1 kilogram mass, which made them squeeze more tightly, which made our force go up.
That's right.
We also saw the other question is what kinds of surfaces are in contact? And so we changed this up by adding the paper underneath.
And instead of the block to the table, we had the block to the paper.
Yeah, and again, we see a difference in the forces.
Yep, that
Yeah.
determines the force. Thing of beauty.
So essentially, more force, normal force, more friction. Okay, we have a proportion here. The more force of friction we have, the more normal force we have, the more force of friction. They are proportional. The properties of the surfaces determine the coefficient of friction, mu.
That's the Greek letter what?
Mu. That's how you say it, mu. Which is empirically determined, thus mu equals the force of friction and the normal force. So it has to do with the relationship between those two things. It's a Sound the Kitty mix. Mew.
Coefficient of friction.
Coefficient of friction. Okay.
Such a cute cat, but look how sharp those teeth are, man.
Fangs. Let's go back one more, Morgan.
Let's do that.
Yeah. Let's go back to this slide. So, one thing I want to point out is that mu does not have any units. As you can see, we have units of newtons here and newtons here, so they're going to cancel each other out. So mu, we do not have to worry about units for it. Sweet. My other question that I want to ask you guys, how can we find the normal force here?
Whoa.
Huh. How can we do this?
Well, what is the normal force?
Well, the normal force is the force being pulled up, right?
Yeah.
Now, isn't it equal in magnitude and opposite direction than the force of gravity or the weight?
It is.
Let's go ahead. We're going to use this scale to find it. Oh, wrong one. Okay, what does it say right there? Is it 5.5?
5.5 newtons.
Okay.
So the force of gravity on that is 5.5 newtons.
Okay, should I write this down?
Well, let's make a free body diagram.
Yeah, okay, good idea, good idea. So, free body diagram. So you just told, we just measured the force of gravity, and it was 5.5 newtons for the block, right?
Yep.
And what does that mean for my normal force? Oh wait, this is gonna be negative, right?
It's down.
Negative. Negative meaning direction. And that means that this is going to be 5.5 newtons. Now we measured, what color did you do this one with?
I usually use black or purple.
Ooh, purple.
So we got the normal force. Now we need to find the force of friction.
So if we want, if we want to calculate mu, we need the force of friction. Now,
But what do we have?
know? I think that we know this one, right? Because it's when we were pulling.
Yep, that's a force of the pull.
Force of the pull, 3.8 newtons. Now that's going to be
Okay, that was
equal-
just before it moved, so it wasn't moving, right?
Yeah,
So if it's
just
not moving,
before.
what do we know?
We know that this is static, right?
Yeah.
We're talking about the coefficient of friction, but static.
It's going to be
mu.
static. What else do we know if something's not moving?
Oh, if something is not moving, then it's also going to have an acceleration of 0. Yeah?
You love your
Oh, I know.
sweaters.
I can watch it, right?
That's true.
So
yeah,
the
you're right.
acceleration equals 0, which means my net force is 0 too, right?
What does it mean if the net force is 0?
That means that everything needs to cancel out.
Oh, okay. So what's canceling out so far?
So right now these two are canceling out.
Yeah.
So we need something to cancel this one out.
How about
The force of friction. And that should be equal but opposite.
3.8 newtons?
So this means that we can calculate it, yes?
Yep, we got the force of friction. We got the normal force. It's just the top divided by the bottom.
Let's do it. So mu equals the force of friction divided by the force. So our force of friction is negative 3.8 newtons divided by the normal force, which is 5.5 newtons. And I get 3.8 divided by 5.5. No, I didn't put the negative number in there, but does it matter? Got
We can talk about that.
So 0.69, no units.
It's a dimensionless quantity.
Yeah, we don't care about the units, dimensionless quantity. Who cares?
What is the coefficient of friction anyway? Does it matter if it's positive or negative?
It doesn't. It's irrelevant. It's the properties of the surface that determine the coefficient of friction. The
That's
fact that it's negative is irrelevant.
Yep.
Doesn't matter.
And the properties of the surface aren't either positive or negative. They're just there.
Okay. Mew.
Kitty, kitty.
This is the standard form for the equation. And notice how simple it is.
It's pretty simple. A is equal to B times C.
Yeah, it's easy, right? So, look at that. So here we have a whole chart full of different mu's.
Yep.
And we have 2 different columns because we have 2 different types of
I
forces
notice a
of friction.
pattern here. I notice that one is bigger than the other for each one.
Oh, yeah. So more bigger over here, less big over here. What does that mean?
Coefficient of static friction is bigger than the coefficient of kinetic friction.
Why
We
is
saw
that?
that when we with the scales, because when we were pulling, it got bigger and bigger, and then when it started to move, it was less.
Yeah.
Remember that?
Yeah, it took us a lot more force to move it when it was sitting still.
Yeah.
But once it was moving, it was like it
It
bounced
was
way
less.
back down.
That's because the coefficient of kinetic friction is less.
Ooh, a practice problem. A 1 kilogram box is sitting on the floor at rest, while a horizontal force of 50 newtons pulls to the right. Make free body diagram showing. Oh, I probably should have left that.
Yeah.
Showing all the forces. That's okay. We'll start over. Okay, here's our box sitting on the floor. It's at rest, chilling. Now, if it's at rest, it's not moving, no acceleration.
Net force is 0.
Net force should be 0.
So
So
if
10
it's
kilograms
10 kilograms, what's the weight going to be?
times negative 10 equals negative 100 newtons.
Sweet.
Okay. Normal force. The opposite of that is just 100 newtons. And how much am I pulling it?
50 newtons.
50 newtons. About half the size of the arrow. Oh, normal end. And
Have we got all the forces now?
Not yet. Okay, these have to be equal to each other as well. And what is it going to equal?
There you go.
There we go. Okay, here are all of our forces. What's next? The same box, this box, is now pulled at constant speed by a horizontal force of 45 newtons.
Oh, okay, so what do we have to change on our diagram?
Well, we have to change this, right?
Yes, ma'am.
So now it's 45 newtons. And we want to know the mu. What was our equation again?
Force of friction over force normal. You're gonna have to change that.
Oh, this guy over here, right?
Now, what does it mean if it's being pulled at a constant speed? What does that mean?
Constant speed, that means we have an acceleration of 0.
And if the acceleration is 0, what does that say about?
Then that means that our net force is also 0. So our force net is 0. Our acceleration is 0. And we said constant speed.
Yep. So that means everything cancels out, up and down, left and right.
It needs to look like this. Everything needs to balance out. Okay, so we're trying to figure this out. Do we have our force of friction here? Yes. Negative 45 newtons divided by, what's our normal force here? 100 newtons.
I don't think you need a calculator for that.
Negative 0.45. Does the negative matter?
Doesn't.
You can leave it, you can take it out, it's up to you.
All harm, no foul.
Is the number.
Sweet.
Sweet. And I think
that
that's it? You guys have some homework though. You guys are gonna do, in the book, oh actually, I'm gonna have to upload some pictures of this for you guys because you do not have this book. But here's what I want you to do, just so you know. So example problem, running over your foot, flat tire. So 131, start here, example problem. It finishes over here. Then do this one as well. Finishes over here. And then the practice problems on page 133, 14, 15, and 16. And you know what? You can actually find these on the library eText page on our website. Go to the website, go to library eText, and I think it's Principles 2002. But I will still put a picture for you guys, just because I'm that amazing. Okay. All right, that's it. That's all I've got.